right. Hi, everyone. Thanks so much for coming in. I promised myself I wasn't going to start this by saying all right, because I feel like I say that every time I start this, but here we are. Welcome in. Thanks for joining us tonight. We're here for a graduate student talk with Swati Ravi at the List Visual Arts Center. So thanks so much for joining us. This is a series where we invite graduate students to expand our exhibitions and their expertise in a similar subject matter as a way to see how art and research are overlapping on MIT's campus. Tonight, we'll be hearing from Swati, a physics PhD candidate at MIT, focusing on some of the universe's most extreme objects, black holes and neutron stars. Her research utilizes space telescopes to analyze X-ray light, mapping the structure and geometry of these cosmic bodies. Additionally, she helps develop and test hardware for future space missions in MIT's X-ray polarimetry lab. She holds an undergraduate degree from Columbia University and a master's degree in space science and technology from University College Dublin, where her work included research projects for NASA and the International Space Station. In this talk, Swati will connect Brittany Nelson's artistic practices inspired by space exploration with scientific methods used to study black holes, highlighted the shared roles of imagination, inference, and uncertainty in making the unseen legible. At the end, we'll have a Q&A where you have a chance to ask any questions you may have. With that, thank you so much for being here and showing interest in our programming. And I'll hand off to Swati now. Thank you.
Thank you for the introduction, and thank you to the List Visual Arts Center for the opportunity to speak with you all today. What goes up must come down. This is, in its simplest terms, the law of gravity. Gravity governs the universe on all scales. It is the glue which keeps our feet planted to the surface of the Earth, and it is also the force which holds our sun together, even as nuclear reactions blast out from deep inside its core. But this balance between the outward push of pressure and the inward pull of gravity in any star, particularly our most massive ones, is a finite dance. After millions of years, these massive stars will burn through all of their nuclear fuel, finally allowing gravity to win this tug of war and collapsing the star into a fiery explosion that we call a supernova. When the dust from this has settled, these stars will have turned into one of two things. The smaller of these massive stars will have turned into neutron stars, balls of matter so tightly packed together that one spoonful would weigh as much as Mount Everest. And the larger of these stars will have transformed into the most gravitationally powerful objects we know in our universe, black holes, from which not even light can escape. My job is to study the environments around these black holes and neutron stars. This is complicated by the fact that these systems are pretty small, pretty faint, and pretty far away. In the right circumstances, though, a black hole might form close enough to another star such that the gravity of the black hole can begin to pull off the gas from this neighboring companion star. And as this gas spirals further and further inward, closer to the black hole, it will begin to heat up to millions of degrees, glowing brightly and becoming observable by telescopes in space that can see X-ray light. While it would be wonderful to look through a telescope and see the black hole and its companion in this beautiful binary, even our best telescopes of today have no hope of resolving this structure. Instead, we infer this picture from a rather unremarkable blob of light that looks something like this. The secret behind going from the blob to the beautiful artist illustration is to use a property of light called polarization. It works like this. Each particle of light coming from the hot gas around a black hole vibrates as it travels. Far away, these vibrations can point in random directions. But as the light bounces around the structures nearest the black hole and is steered by the black hole's intense gravity, these vibrations begin to line up in organized ways that retain an imprint of the overall structure of the environment that we can use to reconstruct this picture over here. What I'm most interested in is how these signatures change with time. This is a fairly complicated endeavor. If you've ever tried to take a picture of something, especially moving at night, you'll probably be familiar with the blurry mess that results. In environments with low light, we generally try to compensate by taking a longer exposure photo. And in the world of these black holes, when I say longer exposure, I mean it can take us sometimes weeks just to take one picture. But ask a black hole or a neutron star to sit still for a week, and you'll find that they often won't comply. The resulting image will take on a character not unlike what we see in the image entitled Candle in the exhibition today. In this print, we see the profile of a woman's face, illuminated seemingly only by the light of a candle. If you look closely, you'll notice that the flame takes on an odd character, its form hazy and somewhat distorted, because the flame, like a black hole, has flickered and moved and refused to sit still for the duration of the static image that was captured. And so rather than a crisp image of the structure of the flame at one pinpoint in time, we instead see a superposition of the many different shapes it danced between over the duration of the exposure. My work seeks to take static images like this and try and reconstruct the movie. I do this by assuming that the light evolves in some predictable way. For a candle, we might imagine the flame flickering left and right. And I can then divide my long exposure into millions of individual frames, each with just one particle of light. Alone, each frame is pretty meaningless. You won't see anything at all. But I can begin to rotate each of these frames where I think the light has wiggled somewhere back to some shared reference orientation and stack them all back together. And then, if I have done things right, the hazy blob of light will sharpen and reveal the detailed structure that we couldn't see before. Applying such a technique to a neutron star, I begin to be able to understand how the hot plasma distributed around the neutron star, which we call a corona, takes shape. In the hazy preliminary image that one space telescope took of one particular neutron star, it was unclear to tell if the corona took on the shape of a spherical shell that encased the neutron star, or instead took on a more spread out and horizontal geometry. But by reconstructing the movie of how this neutron star changed over time, suddenly the hazy image turned clear. And for the first time, I could see that the corona took on the extended and horizontal geometry rather than the compact and spherical one. But sort of hidden in this work is the kind of pesky detail that my reconstructions are based ultimately on a guess of what could be going on in these systems. I can try to reconstruct an image several different times, each with a different guess of the behavior of my source. And I can compare each of these reconstructions quantitatively and see which fits the data the best. But at the end of the day, the reconstruction can only ever be as powerful as the scope of my ability to imagine what could be going on around these black holes and neutron stars. Here, I am confronted with the sort of central tension of the way in which we usually tell these scientific stories. It is easy to think of this process as deterministic. We point a telescope, we take a picture, we look at it, and suddenly the structure of the universe has revealed itself to us. It is especially tempting to do so because we increasingly pool our efforts in the astronomical community into bigger and more powerful and more expensive telescopes. In the film playing over here, Brittany Nelson has captured a sort of eldritch quality of one particularly enormous telescope at the Green Bank Observatory. She likens the telescope to an ex-girlfriend haunting her. And seen from these less common angles, from the back, like in the photograph behind us, or from afar, the telescope takes on a domineering quality. It's transformed beyond a mere instrument to aid in our science into something larger than life, some infallible and supernatural being that can speak the truth of our cosmos. Interspersed with the footage from the Green Bank Observatory in the film are quotations from the 1938 novel Rebecca by Daphne du Maurier. In case you're unfamiliar, the book follows an unnamed female protagonist who is haunted by the lingering memory of her husband's late first wife, a woman named Rebecca. But much like the Rebecca of the novel, this larger-than-life character taken on by these telescopes is only ever an imagined one. Up close in the film, the facade breaks. We can see the rust and the chipped paint of the telescope's support structures. The Green Bank telescope, like all telescopes, is imperfect, biased in what colors it can see and where we choose to point it and what we choose to do with the data. I work almost exclusively with telescopes we send to space because the light I'm most interested in gets absorbed by Earth's atmosphere. And just as the Green Bank telescope succumbs slowly to the forces of nature on Earth, like rain and rust, the telescopes we send to space will, for a time, brave the brutal space environment, but will ultimately also fall apart. In 2004, NASA launched a telescope named SWIFT to outer space in a zone called low Earth orbit, some few hundred kilometers above the surface of the Earth. In the 20 or so years since then, this telescope has been observing the sky and producing amazing scientific images. But it cannot escape the inevitable pull of gravity, and so it has fallen lower and lower over time. If uncorrected for, this telescope is set to fall far enough to burn up in Earth's atmosphere just later this year. What goes up, we must remember, must also come down. This is the law of gravity. More recently, in 2017, NASA launched a telescope named NICER to live aboard the International Space Station. A few years later, some debris struck the outside of the telescope, puncturing it and causing extra light to leak into the telescope. Because NICER lived on the International Space Station, an astronaut was able to take a spacewalk and slap some patches over these holes. All seemed well. But on June 17, 2025, the motor used to point the telescope at targets in the sky gave out, and so the telescope became no more. What do we do with the dead telescope in space? Well, the body of the NICER telescope still sits at the edge of the International Space Station. It will likely live there until the space station is decommissioned in the next 5 years or so. As part of this decommissioning, we will begin to allow the space station to succumb to its tendency to want to fall back to Earth. And then we will attempt to guide it the rest of the way with a rocket, such that whatever pieces survive the fiery reentry process will land somewhere in the Pacific Ocean. It's easy to think of the story of this telescope ending here on June 17, 2025. But what survives is an expansive and remarkable archive of the various black holes and neutron stars it once pointed at. NICER looked at one such black hole over 100 times. This particular black hole lives in one of our nearest neighboring galaxies, called the Large Magellanic Cloud. We point to it often because in the scale of the whole universe, it's pretty close by. And also because it doesn't live within the plane of our own galaxy, the Milky Way, we don't have to look through stars and dust and other stuff. We have a pretty clean line of sight to it. The black hole also has stable behavior over time, and so because the NICER telescope has pointed at it so often, we now have an astounding archive of snapshots of just this one black hole. Another facet of my work is to return to these 150 or so snapshots of the black hole and perform a sort of retrospective with all of these individual observations stitched together. I can begin to pull out a more clear picture of what might be going on with this accretion disk of hot gas. A lot of our current understanding of these disks comes from theoretical predictions, which make simplifying assumptions about what exactly is going on. We draw this disk as a perfect, near two-dimensional circle of hot gas, ignoring the complicated and messy ways that this real picture might deviate from the idealized imagination. And so in this way, the legacy of the NICER telescope lives on in its archive, even after it can no longer collect new light. And this is the fate that has befallen the many generations of telescopes that were used before our modern fleet. It is an arduous but paramount task to maintain the archives of these telescopes, and it is exponentially difficult to do so in the time before we could store this data digitally. I'd like to zoom us out now back to the early days of photographing the night sky. We're talking like the late 1800s. In this time, you'd need to dump special chemicals onto small squares of glass and place the glass inside a telescope. The chemicals on these glass plates would react with the light collected by the telescopes and produce an image negative, a physical one that you could hold in your hand. Just down the road from here, we have one of the world's largest collections of these historical telescope glass plate negatives, the Harvard College Observatory's astronomical photographic glass plate collection. If you visit the collection in person, and I really recommend that you do, you'll find shelves upon shelves of these glass plates, tucked in sleeves and stored like books in a library. There's over 550,000 of them. They range in size from about the size of a piece of printer paper to about the size of a vinyl record. It is impossible to tell you the story of these plates without telling you at least a little bit of the story of the women behind them. Between the 1870s and 1970s, at least 200 women worked with these plates. They were known as the astronomical computers, a title designated at the time for people and not machine. These computers classified over 10,000 stars. They discovered countless nebula and galaxies, and even identified the first white dwarf stars. They did this through tedious and tough work. The imaging process for these plates wasn't easy. You had to rinse off the chemicals once the plates had been exposed, and some of these plates are rinsed off in such a hurry that streaks of chemicals are still smeared along the perimeter of the plates. They also collected dust and debris, and these computers would sit and look at each speck of dust on each plate and carefully try to identify if it were a star or a galaxy or just a speck of dirt. These plates often had annotations made by the computers. Look closely, and you'll see handwritten numbers and letters designating various classifications and hand-circled objects of interest. Like so many other areas of society, the work of these women was undervalued. Despite having degrees in astronomy, they were usually paid around 25 cents an hour, substantially less than their male colleagues. There was little chance for upward mobility through promotion and little opportunity to do anything besides this tedious work. One astronomer, Cecilia Payne Gaposchkin, analyzed the glass plates at the Harvard College Observatory as a graduate student. She discovered, kind of astonishingly, that stars seem to be composed predominantly of hydrogen and helium. This was particularly surprising because the leading scientific theory at the time was that stars should be composed chemically nearly identically to the chemical composition that we see on Earth. And so at the urging of her thesis reviewer, she wrote that these results were, quote, almost certainly not real. 4 years later, the reviewer realized that these results were real and rewrote the discovery under his own name. The efforts to remember and recognize the work of these computers continues to the present day. From 2004, the Harvard Plate Stacks team began the endeavor to digitize the collection of glass plates. In 2016, it was decided that before the high-resolution digitization process would take place, the plates would be cleaned, a euphemism for scrubbing the plates of the handwritten annotations made hundreds of years ago, carefully and painstakingly by the astronomical computers. The effort was brutal. The plates were wiped with Windex, and then when it was realized that the blue dye was damaging the plates, the annotations were instead scratched off, one by one. It went in this way until 400,000 of these plates were stripped of their annotations, stripped of their history and of their science. We come now to the elephant in the room. This photograph behind me is of a broken astronomical glass plate from this collection. If you look for this plate on the shelves of the plate stacks, you'll find an empty sleeve about the size of a vinyl record with handwritten notes by the astronomical computers. From these notes, we know that the plate was originally taken and annotated in Peru in the early 1900s and was then broken in August of 1909. The writing on the sleeve notes all of this and also the name of the person who committed the offense of breaking the plate. And at the top of the sleeve is a note that reads, "Plate too badly broken to be mended, pieces packed in an 8x10 box." For over 100 years, the shards of this broken glass plate have been carefully preserved. The quality of the reconstruction still good enough for the plate to still be used for science. Perhaps because it was broken, the annotations are still intact on this plate, and I invite you all to take a closer look at them before you leave. I wish I could tell you that the world 100 years later is now welcoming to the marginalized people in our academic communities. But even this year, graduate students of color are kidnapped in our neighborhoods surrounding the campus in the name of immigration enforcement. And even in our own physics department, graduate women are the target of a harassment campaign organized by multi-million-dollar extremist organizations that take offense to our recognition of the existence of transgender and non-binary people. It is easy to look at all of this and wonder if our contributions in this generation will be doomed to the same fate as the glass plates, if our work is to be wiped clean of our names in the next century. Perhaps we, like these telescopes, might be destined to crash back to Earth. But I am reminded of the extraordinary perseverance of the astronomical computers, whose work continues to be foundational for our understanding of the universe. And I'm also reminded of the extraordinary preservation effort for this one broken glass plate. And I hold hope that for whatever parts of us break, that there might still be people who care enough to pick up the pieces and keep them safe in a box somewhere for another time. The universe rarely sits still. Stars collapse into black holes. These black holes flicker and evolve. Glass plates slip out of hands and shatter. Telescopes fall from the sky. These things cannot be undone. We can never get back the annotations on those 400,000 scraped glass plates. But we do have a choice with what to do with what we have left. When telescopes leave behind their archives, we can continue to squeeze them for scientific insight still hidden within. When our data is destroyed, we can work to repair and preserve it. And for the glass plates still left with their annotations, we can turn a new leaf. In recent years, the Harvard Plate Stacks team has found a non-destructive way to image the glass plates without touching the annotations. Imaging the plates in infrared light, as it turns out, renders most of these annotations invisible. Perhaps poetically, it's a technique that we've long known in the world of astronomy, to peek through the cosmic dust and debris using different wavelengths of light. When you look at the work in this exhibition, I invite you to appreciate the ways in which Nelson has captured the sublime and imposing enormity of the Green Bank Observatory, and also how she has captured the humble fragility of the broken glass plate. I hope that I have convinced you that in my line of work, these are not contradictory ideas. Even the greatest telescopes that we build to study the universe are, after all, governed by the very laws of physics they seek to uncover. Our efforts to map the universe are ambitious and seemingly superhuman at times, but the stories these telescopes tell us will always be warped and distorted by the human eyes and hands that touch its data. Things will break and decay and die, but if we are intentional, we might choose to curate and conserve some fraction of this work, because it is worth remembering the messy and imperfect and human effort that lives behind each story that we tell about stars and black holes and galaxies. The novel Rebecca opens on our unnamed female protagonist, reminiscing about her former life in a beautiful mansion, now burned to the ground. She recognizes that this home, like the glass plate annotations and the dead telescope aboard the International Space Station, can never really be brought back. But she also realizes that some part of these things will always live on in the memories that she holds of them. She says, "I am aware of a sense of loss. This has been ours for however brief the time, and we leave something of ourselves behind, nothing material, but something indefinable. The house sheltered us. That was yesterday. Today, we pass on, we see it no more, and we are different, changed in some infinitesimal way. We can never be quite the same again." Thank you.